What every product manufacturer understands is that as you iterate the product, you try and remove the ingress gaps that are vulnerable to liquid and dust, and these gaps being removed leads to the completion of the final product. The importance of this is as you start to scale up the manufacturing process of that product, you start to identify crucial potential bottlenecks, and these components are going to be supplied by a company. And the company that potentially supplies this critical component to Tesla, Figure AI, Boston Dynamics, Unitree, Xpeng, and many more as they scale their product, the humanoid, will become vital to the production of the humanoids in this sector in the future. Who is going to supply these critical components is that big question. How are the humanoids going to have longevity and durability whilst also being able to carry out the movements and motion that are required to do everyday tasks? To answer this, we have to delve deeper into the rotary versus linear debate as the two leading options for the actuator movement to allow for robots to move and carry out direct, precise actions. It's either going to be through a rotary movement, which is going to be an angular motion, or it's going to be through a linear movement, which is a push and pull and forward and backwards movement. However, this could lead to a crucial bottleneck, as if you are a robot maker and you use the linear actuator movement, you're going to need the critical component called the planetary roller screw. If this is not strategically planned for, it could be the limiting factor in their ability to scale and capitalize on this humanoid robot total addressable market. This planetary roller screw is going to be a component that's going to be potentially a bottleneck for any robot maker using linear actuators. And you might think, why don't all robot makers just use rotary actuators that don't require this irritatingly valuable, scarce screw? Well, most robot makers do. But there are trade-offs to using that engineering approach, and linear actuators still have a place, and therefore you're going to need that planetary roller screw in order to build those actuators and scale up those humanoids that use those linear rotary screws. In this video, I'm going to look at the planetary roller screw in detail, look at why it is a potential bottleneck. I'm going to look at the linear versus rotary debate and why there are benefits to using both. And there is not just a simple, we just go with the rotary actuator because they're easier to create. There is going to be trade-offs. Linear actuators have a place, even though they're going to require this extremely important component. There's still a place for them. Then I'm going to finish off with how could all of this be relevant, especially for Tesla, who use a combination of rotary and linear actuators. This information and the prompt for me understanding planetary roller screws being a potential bottleneck for future scaling of humanoid robots came from the robot expert Scott Walker, one of the most incredible follows on X. He's called the humanoid pathologist, and he is extremely insightful when he comes up with this research and these threads, especially for humanoid robots and what's going on in all of the different companies within the sector. So if you like videos on humanoid robots and innovation, this is part 2. Like, comment, subscribe. Let's go. Okay, let's have a look at the inside of the planetary roller screw. Inside this cross-section of a motor is a threader screw. Around this screw, small, thin rollers spin around it like planets, creating the push and pull motion. This is perfect for robot arms and heavy machines. They're converting the rotational movement into linear movement. The iteration of innovation for the humanoid robots has become more developed, and therefore they're trying to optimize for power efficiency, reduce the overall weight, and then also optimize for the way they use their space. So when they use these linear actuators, they've started to make them even smaller. Inside the robot is the interior rotary screw, this smaller version of the linear actuator, and this is used in the Optimus. The most important component here is the planetary roller screw on the nut house because this creates the motion. The rotation is causing the axle to move forward and backwards, and then the contact bearings help stabilize this motion. An example here is the Optimus design, where you can see the linear actuator powered by the planetary roller screw is being used to help straighten the knee as it stands up, and then also relax and collapse the knee as it comes down. So you think about that push and that pull and that forward and that back motion is being created through rotational planetary roller screws that go around and slide around that threaded screw, and that moves the motion forwards and backwards. And that can be extremely useful, especially when you're trying to lift the load, because that push and pull is going to allow you to lift a heavier amount of payload. That leads to the bottleneck problem for the planetary roller screws, because if these linear actuators are going to be in high demand and useful, then these planetary roller screws are also going to be extremely necessary to be able to scale up humanoid robots that use these designs. Each linear actuator needs about 10 to 12 planetary rotor screws. This can add up to 40 just for the lower legs of the Optimus. 1 million Optimuses would require 140 million planetary roller screws. The machines making them are highly precise and only produced in the single digits. Therefore, if you were to continue to scale up to 1 million Optimus robots, which is what Elon's comp package is going to require him to do, and that's what they're guiding for, that would require 1 billion planetary roller screws in order to satisfy this demand and this scale. This is proven to be a potentially critical component. So when you break down the components for the bot, it's going to need cameras, batteries, electronics, and actuators. You could just ask the question, well, if the screw is the most important part of this actuator design, can't I just buy these screws in high volume on Amazon? Well, the precise equipment required to make one of these screws is extremely expensive and extremely complex. It's not that simple because the actuators are designed to bespoke robot architecture involving a series of supporting components such as magnets, windings, gearboxes, transmission systems, and integrating these systems reliably is going to be extremely bespoke for that exact humanoid robot design. When you deconstruct this process, the critical component becomes the planetary roller screws. It is a desire for every successful company to be fully integrated for the cost savings and efficiency. However, when you know that this planetary roller screw is going to be so vital to the actuators that you're using for your humanoid robots, you realize that the tooling required to make these planetary roller screws is extremely high cost of entry. It's a highly precise equipment that produces these single-digit screws. So you need a lot of them, you need a lot of capacity, and so it's hard to be vertically integrated in this particular field when you need this component. Therefore, you might need to outsource this component. However, the problem becomes a company that's going to start to invest in the facility, the capacity, and the equipment to scale these planetary roller screws needs to know that there's also a big demand. Then there's going to be a lot of companies that are going to require this component, because if they invest in this component and the facility and the tooling to make it, they're going to want to be able to make a high return and a high gross margin from this particular component. And therefore, it becomes difficult unless you actually have the contracts to be able to say, okay, we're going to need 1 billion planetary roller screws over 5 years. Will you be able to provide that? And if you've got that type of contract from numerous robot companies, or you'll be extremely motivated to be able to start building the facility to provide that particular component. Now let's look at the debate between linear and rotary actuators. Now, linear actuators use the planetary roller screw, that rotational movement. The planetary rollers go around that threaded nut house screw, creating that forwards and backwards motion. Whereas rotation actuators already have that built-in rotation actuator, that built-in rotation motion, so they don't need this planetary roller screw. There are companies that are using just linear actuators, and there are companies that are using rotary actuators. And then there are companies such as Tesla that are using a combination of both. And there is a reason for that. The linear works by using the rotational motion from the planetary roller screws to glide along the interior screw and create a forward and back motion, good for pick, place, push, and pull. The rotational actuation is using pneumatic or hydraulic energy to create a circular angular motion. This is good for the freedom of movement for that humanoid robot in that actuator joint, and also more creative motion as you can move the robot in unnatural ways that are different to humans. Now let's look at the linear advantages. They are great for precision of movement in the industrial equipment, bound by specific parameters and position, inserting and removing. They are cost efficient, they are reliable, used for automated systems that require control because the parameters are easier to specify when that movement is forwards and back. They are designed for very defined strokes and fast responses, can produce high force, good for repeatability of a task, good for compact design and durability as they are versatile. So that simplicity of design can lead to lower maintenance costs and longevity and durability, which is the aim for these humanoid robots if they're going to be doing productive, useful tasks over a long period of time. However, there are some serious drawbacks to using just linear actuators. And that's why Tesla's Optimus robot, where they had linear actuators, had a disadvantage when it came to training the synthetic simulated data and turning it into real reality learning. Because you think about rotary actuators have more freedom of movement. There's more creativity in the way that they can pick and place objects and maneuver their environment. Because they have more freedom of movement, it's a lot easier to use synthetic training data and then convert that to real world data where they can actually go around the environment. With linear actuators, there's more friction within the real environment. So there's a gap between the simulation and then that robot being able to use the simulation in real life, in a real environment. So linear actuators have that complex kinematics, difficult to model and simulate. This hinders their reinforcement learning. It's hard to create rotational movement as it has non-linear torque. It's less predictable performance. It's limited in its range of motion. The torque, its ability to power rotational movement, is limited because the movement is going to be very similar to a human. There's not going to be as much freedom of movement, but that also might be an advantage when it comes to power efficiency and being able to optimize for durability and longevity. Now let's move on to rotary actuator benefits. There's more degrees of freedom in their range of movement, and this is one of the most vital parts. This can create repeatable motions like spinning, and it allows the actuators to be able to travel at an angular path. That motion at an angular path is so vital. It's useful for when you want to turn products on an assembly line because of that range of motion. High levels of torque can be offered with that rotation, so you can turn things a lot quicker and with a lot more power. However, there are disadvantages because to achieve this higher level of torque, they need to be bigger, reducing the ability to optimize for space in the robot design. There's higher cost to train as there's more complexity in the advanced controls needed to control the countless angular motions that you can have and you can simulate for so many different angles when it comes to rotary actuators. There's higher susceptibility to wear and tear, and this has been noted in the Unitree engineering where they've had reported instances where their actuators just have not been able to have that durability and longevity over a long period of time. And therefore, when you start to go into the utility of the robot, if you're optimizing for movement and that ability to use rotatory actuators, then you might be making the trade-off of being able to have longevity and durability in the robot design. And it might be less optimal actually having all of these different angular movements and these different ranges of motion and trying to create different ways to stand the robot up, like in Boston Dynamics example. And it might be easier just to have a linear movement that can handle load, can handle durability, and can stabilize for longer periods of time. The potential of having to undo this engineering could lead to real extreme setbacks in the future. The training data could lead to hardware challenges as this movement isn't compatible with human movement. So if you think about training a robot to be similar to a human and manipulate a human environment, you might have to undo a lot of this engineering, which could be extremely cost inefficient in the future. An important insight on how to choose between linear and rotary, or a combination of both, is thinking about the case study that is Apptronik. They've been in the business for 20 years. They are the most advanced and they've put the most research and development into the actuator design. They've got the smartest actuator engineers on the planet, and they've been doing this for 2 decades. And they've come to the conclusion that actually using linear actuators is the best approach, even though the market's currently going for rotary actuators. And that might be because of the limitations in this critical component, the planetary roller screw. And when you have that critical component as a bottleneck and you can't manufacture these at scale, these robot companies that are going for the rotary actuators are probably deciding this based on how can we scale quickly? Do we need to have this critical component prevent us from being able to build mass amounts of these robots at scale now? You've got Medea, who are the largest appliance manufacturer, and they've got a robot division, and they're using a mixture of both linear and rotary actuators. And then you finally got Tesla, who are using a mixture of linear and rotary actuators in specific places where they might be optimizing for movements that could benefit more from rotary and then movements that could benefit more from linear. And when I come to deciding on where my investment should go or where my understanding of the confidence I have in engineering, it's usually going to be with the smartest engineers. And Elon has proven himself to be able to understand the potential problems ahead of time and design, for example, the fully self-driving software using just cameras and sensors rather than this sensor suite that Waymo for Google use, these extremely expensive LiDAR technologies that are extremely complex, expensive, and don't actually provide the same level of sophistication on the roads. Elon's ability to engineer for the future is what I am putting my faith into, because I believe that he's managed to source the right team and find the most optimal utility-based robot that can be used for everyday tasks and be productive and actually be used in a house for domestic jobs and also in factories for pick and place, repetitive movements, precise actions, and being able to do that for a long period of time. So, could it all be relevant? I think that the final part of this is just understanding that as you start to look at innovation, as you start to look at these sectors that are emerging and may seem fictional for a lot of financial analysts on Wall Street and these big financial firms, you start to realize that the bottlenecks could also open up an opportunity. If most robot companies are going with rotary actuators, Tesla are going with a mixture of both, Aptronic are going with linear actuators only, there's going to be this critical component. And if that becomes a component that is manufactured by only a small minority of companies, those companies could present real opportunities for future investment, because it's just going to be similar to NVIDIA. They provide all of the GPUs, the B200s, the H100s, the H200s for all of the data centers, all the big tech companies. When you have a monopoly, you have extreme growth. This growth is crazy. And so planetary roller screws is something that I'm going to be looking into more and looking for companies that source or provide the tooling or provide the ability to scale up for these large robot companies that are going to rely on these in the future. But when you think about embodied agentic hardware that's going to move around from cars to humanoid robots, you've got to think about the longevity of the engineering. And as you scale up, you're going to find that there's going to be changes that you need to make. And currently with Tesla, they have a version 2.5, this gold colored humanoid robot, the version of Optimus is very similar to Generation 2. But Generation 3, according to Elon, is going to be extremely different in the way it looks. So maybe they've managed to solve the most optimal placement and positioning and space optimization and power efficiency and reducing the weight perfectly so that it can be a robot that can be lightweight, domestic, in a house, and safe. Maybe they've managed to find the correct combination of linear and rotary. But the jury is still out on whether it's the right decision to go fully linear or it's the right decision to go fully rotary. But I have confidence in an engineer who's managed to solve so many of these difficult problems, from being able to have the chopsticks that catch the Falcon rockets that come back down. That engineering, when it comes to fully self-driving and using just vision only, that engineering when it comes to Neuralink, the boring tunnels, the Cybertruck design using this SpaceX metal and just being able to cast it and create it within seconds, that engineer and that engineering team is who I believe have managed to solve potentially the ability to scale out humanoid robots. So planetary roller screws, a very critical component. There's a combination of companies that are using just linear actuators and then also just rotary actuators, which is the most popular at the moment with the robot makers. And then there's also a few companies that are using just a combination of both. Neura and Tesla are using a combination of linear and rotary. So something to think about. But I hope you got some value from this video. This is part 2. The part 3 of this video is going to be looking at the economics, and it's going to be taking Cern Basher's extremely useful work and AJ's extremely useful research when it comes to the scaling into 2026, 2027, 2028, and how disruptive this is going to be when it comes to jobs. And actually, a lot of companies will be able to absorb a lot of these robots before it actually starts to impact people's lives in a negative way when it comes to disrupting your job, disrupting your ability to work and find work. And so I hope you got some value from this video. I hope it helps you understand the mechanics behind humanoid robots, from the different combinations of the movements from flexion, abduction, rotation, and then also the different types of actuators that are going to be used to create those movements and how that can be impactful to the longevity, durability, and freedom of motion and simulation and training of the humanoid robots. So like, comment, subscribe. See you in the next one. Thank you very much.